Welcome to the Explainer. Imagine, if you will, you're tasked with organizing a massive, multi-volume dictionary. Now imagine if every single time words shared the same starting letters, words like apple, app, and application, they actually shared the exact same physical space on the page to save room. It sounds kind of like magic, right? But in the realm of computer science, this is exactly what we do to save memory and drastically optimize our software. So, think about it. How can we store millions of overlapping words without just completely wasting space on shared prefixes? If you try to store all these words using standard arrays or hash maps, you're going to hit a wall pretty quickly. They are just incredibly inefficient for prefix searches. I mean, storing the letters APP thousands of times over for thousands of different words, that leads to a massive problem of redundant data storage. We desperately need a way to overlap these shared prefixes structurally. Well, enter the trie. It's often pronounced trie, though some say tree, but it's also known widely as a prefix tree. This is our hero data structure for today. It is designed specifically to solve this exact redundancy problem, and it does it so elegantly. By reusing shared nodes, a trie supports remarkably fast insertions, exact word searches, and prefix matching, all while keeping our memory footprint as absolutely tiny as possible. Here is our roadmap for the explainer today. First, we'll meet the trie. Then we'll dive into inserting words step by step. After that, searching for words, followed by finding prefixes. And we'll wrap the whole thing up with a complexity analysis. Okay, let's kick things off with section 1, meet the trie. Let's start with the absolute foundation. Every single trie branches out from a single empty root node. You can basically think of this root as the starting block of a race. From there, we define what we call a trie node. Each of these nodes represents a single lowercase English letter branching outwards. But, and this is a really big but, there's a crucial piece to this puzzle, the isWord attribute. This is just a simple Boolean flag, true or false, and it's used to tell us exactly when a node marks the end of a complete, valid word. Without this flag, we'd literally have no idea if app was a word be explicitly inserted, or if it was just a stepping stone on the way to apple. Moving right along to section 2, inserting words step by step. All right, take a look at the current state of our tree. Branching from the root, we already have 2 words fully inserted. Top, mapping down T-O-P, and by, mapping down B-Y-E. Notice how the P in top and the E in by have their isWord flags set to true. Awesome. Now, we are going to insert a brand new word, bite, spelled B-Y-T-E. Let's see how it cleverly reuses the existing architecture rather than just blindly building from scratch. So the insert function builds the trie word by word, letter by letter. To insert byte, we start at the root and look at our very first letter, B. We query the hash map containing the root's children to see if B is already hanging out there. And in this case, it actually is, because the word by already carved this path for us. So we simply move our pointer down to the existing node B. 0 new memory used so far. Now, here is where it gets really cool. We do the exact same thing for the second letter, Y. We check node B's children. Does Y exist? Yes, it absolutely does. So we just glide right down the existing path to node Y, saving valuable memory once again. Byte and by are now successfully sharing the exact same by-Y prefix structure. It's like carpooling for data. But, eventually, paths have to diverge. We are currently sitting at node Y, and our next letter in byte is T. When we check Y's children, T isn't there, only E is. So we must construct a brand new tree node for T, add it to Y's children hash map, and then step our pointer right into this newly created node. And it's the exact same story for our final letter E. We look at our shiny new node T. It obviously has no children yet, so we build another new node branching off T for the letter E, and move our pointer down there. We have now fully mapped out the physical path for the word bite. Wait, hold on, we aren't quite done yet. We've reached the end of our word, but we have to leave a signpost. Finally, to definitively tell the computer that a valid word ends right here, we flip the isWord attribute to true on that final node E. And just like that, we've successfully stored byte while recycling the entire prefix from by. Pretty neat, right? All right, let's jump into section 3, searching for words. Now that the maze is built and we really understand how insertions share space, let's look at how we navigate through it for an exact word match. Searching for a word uses the exact same strategy as insertion. We just move node by node down the tree. Let's say we want to search for the word to, spelled T-O. We start at the root, find T, and move to O. The letters exist. But And this brilliantly illustrates the importance of our earlier steps. We absolutely must check that the final node's isWord attribute is true. If we previously only inserted the word top, the O node would exist, sure, but as a stepping stone. Its isWord flag would be false. In that scenario, our search for to returns false because it's not recognized as a standalone, completed word in our dictionary yet. It is a vital distinction to keep in mind.
Which brings us perfectly to Section 4, Finding Prefixes. Transitioning from exact words to finding prefixes shifts our logic just a tiny bit, but it keeps the navigation identical. Suppose we want to check if our trie has any words that start with the prefix by. We call our has prefix function, we trace the b from the root, then the y from the b. The characters traverse successfully. And here is the real magic. Because the path exists, we immediately return true. We don't care at all if y has its isWord flag set to true. A prefix doesn't need to be the end of a word. It just needs to be the beginning of a valid path.
So let's sum that up because it's absolutely crucial. What's the difference between these two core operations? Exact search absolutely requires that the final node's isWord flag is true. Prefix search, on the other hand, just needs the physical path to be there in the structure. It's a tiny, tiny logical difference in the code, but it provides incredibly powerful and distinct functionalities for whatever software you are building.
And finally, Section 5, Complexity Analysis.
Let's look at the receipt and see the mathematical cost of our elegant construction under the hood. Breaking down the math, for time complexity, inserting, searching, and prefix matching all take O of k time, where k is simply the length of the specific word you are processing. It does not matter if your trie holds 10 words or 10 million words. The time to search is tied strictly to the length of the word you are actually looking up. And for space complexity during a search or prefix match, it is a perfectly flat O of 1. No additional space is used to traverse the search term. Notice how the time it takes relies completely on k, the length of the word, entirely ignoring the millions of other words stored in the structure.
So that brings us to the end of our structural journey today. Think about where this elegant node-sharing concept could optimize your next big software project. Whether you're building a snappy autocomplete feature, a spell checker, or just organizing massive data sets, the trie offers a remarkably efficient path forward. Seriously, ask yourself, how many redundant nodes could you eliminate in your own codebase right now by rethinking how you store shared data? Keep building, keep optimizing, and thank you so much for joining me for this explainer. Catch you next time.